2211 Lab 1 Constant Velocity. Purpose of the lab is to observe an object moving at constant speed in a single direction and draw conclusions about its motion with our knowledge of physics as well as compare it to a theoretical model. Physics principles used in this lab are Newton's first law of motion, Newton's second law of motion, and the position update formula. The main result of the lab was that our observed model deviates slightly from the theoretical model due to assumptions being made regarding the surroundings not providing any external forces on the sled. Newton's first law of motion states that an object that is in motion will stay at a constant velocity and move in the same direction unless an outside force changes its path of motion, as seen in the visual representation down below. We're going to use this as a basis for creating our theoretical/computational model of the sled's motion. Newton's second law of motion states that the change in an object's momentum is equal to the net force acting on the sled multiplied by the interval of time that the force is applied. Using this, we can rearrange to give us the velocity update formula, as seen below. We're going to also use this to conceptualize a theoretical model of the sled's motion. In this situation, both of Newton's laws are stating that in the theoretical model of the sled's motion, that since there are no outside net forces, velocities should stay the same. Position update formula is a formula used to predict the final position of an object moving in one direction, using the object's initial velocity, average velocity, and the time interval for which the object is in motion, as seen down below. We're going to use this to determine the experimental average velocity of the sled by using the change of position as well as the time interval once analyzing the video and tracker. Here's a video of our experiment. As you can see, the system is the sled. The surroundings are the track, the air, the hand holding the sled in place, and the magnet between the track and the sled, which provides the push to move the sled. Initial conditions at t equals 0 would of course be initial position of 0 meters and initial velocity of 0.454 meters per second, which is experimentally determined later. Next, I'm going to track the position of the sled between equivalent time intervals in an online tracking program to create a position versus time graph. The yielded position over time graph is below. Once I had all the data, all that was left to do was come up with the experimental average velocity. Average velocity is equal to the change in position over time, but first we have to take into account some important factors. We have to take into account the length of the sled as well as the time of the video the sled began to move. We cannot assume that just because these are initial values that they're 0. To create the theoretical model, I used the starter code provided to us and edited the initial velocity vector to match the experimental observed average velocity, which we just calculated. I didn't adjust the position vector because we are naming it its starting point as the origin. I also had to set the time to 4.134 seconds since this was how long the sled was in motion. I didn't adjust the net force vector because we are assuming that the track is frictionless and there are no outside forces acting on the sled. I also updated the formulas under the momentum principle section just to visually show what values are being used to calculate the updated position and velocity. This is the position versus time graph that the code yielded. Now that we have both the experimental and theoretical models, we can determine their similarities and differences. The similarities are that they both have upward, positive, and linear lines of best fit for their position versus time graph. And this indicates that they both have a positive displacement over a given amount of time, indicating a positive average velocity for both observed and theoretical. The differences, however, is the position versus time graph for the theoretical has a slightly higher slope than the observational model, meaning that the sled in the experiment did not go as fast as it was expected to. In physics terms, it means that there was some outside force acting on the sled that did not allow it to reach its theoretical average velocity. Possible sources of errors are that we failed to take into account the possible air resistance that the sled may have encountered while in motion, as well as the possibility that the track the sled is traveling on is not completely frictionless. Also, we assume that the sled started from t equals 0 with a constant velocity, but actually started from rest and accelerated for a short period of time. What if question? If I were to flip the orientation of my axes, essentially my results would stay the same because all that changes is the direction of motion. This would only affect the sign of the velocity, not the magnitude. So when plotting the position versus time graph, the data points would be reflected over the x-axis, but the magnitude of the slope for its line of best fit would be the same. What does it mean question? No, because the forces that starts the motion of the sled is before the initial time, so we aren't able to determine how many forces were applied before t equals 0.